Welcome back to the deep dive. Today, we're looking into something pretty fundamental. Can these incredibly powerful AI vision models, the vision transformers, actually tackle classic human intelligence tests, specifically mental rotation?
That's right. We're diving into some fascinating sources that really systematically test these big models, ViTs, CLIP, Dino, against tasks pioneered way back by Shepard and Metzler.
Ah, yes, the block shapes. Okay, maybe let's quickly define mental rotation for everyone. It's a classic test.
It really is. It's considered a key measure of human spatial reasoning. Basically, your ability to picture an object in your mind and rotate it around in 3D.
You see two shapes, maybe complex, blocky things,
Yeah.
and you have to figure out, is it the same object just spun around, or is one a mirror image?
Exactly. And that ability to manipulate mental representations, that's where things get tricky for AI. It highlights this core conflict between equivariance and invariance.
Okay, break that down. Invariance is usually what we want in computer vision, isn't it?
Generally, yes. Like, you want the AI to recognize a cat, whether it's right side up, upside down, seen from the side. You want it to ignore the orientation and just say cat. That's invariance. You discard the pose information.
Right. But for mental rotation, you need the pose information.
Precisely. You need equivariance. The model has to preserve the object's orientation somehow, track how it changes, so it can tell a genuine rotation apart from a mirror flip. Total invariance would actually break this task.
So it loses the vital clues if it becomes too invariant. Interesting.
Yeah.
So our mission today is, well, first, can these models, often built for invariance, actually learn this equivariant property needed for mental rotation?
And second, if they can, where does this ability actually live inside the model? Which layers are doing the heavy lifting?
Okay, so how did the researchers actually test this? What was the setup?
It was quite clever. They didn't just rely on the model's final classification output. They looked inside.
Probing the internal representations, the embed.
Exactly. They took pairs of images, say two rotated versions of the same object, or an object and its mirror image. They fed both images through the same vision transformer.
Okay, same model processing both.
Then they took the internal embeddings generated for each image and used a lightweight classifier, a Siamese network, basically, to compare them.
To ask, are these embeddings similar enough to be from the same object, just rotated, or different enough to signal a mirrored object?
Precisely. It isolates whether the model's learned features inherently capture that crucial geometric pose-related information. It's a test of the representation itself.
Smart. Okay, so which models were put through this test? You mentioned VNE, CLAP.
Yeah. 4 main families, all based on the vision transformer architecture, but crucially with very different training backgrounds. You can sort of group them.
How so?
Well, you have the traditional supervised model first. That's Google's ViT.
Trained on ImageNet, lots of labels.
Right. Trained to classify objects. Its whole goal pushes it towards that feature invariance we talked about, which you'd think would make it struggle with this task.
Okay, makes sense. And the others, the self-supervised ones.
Yeah. First up is CLIP. It learns by matching images with their text descriptions.
So it has to understand the visual scene to link it to text.
Yeah.
Maybe that helps preserve details.
That's the idea. It might need to keep richer visual cues, potentially including pose or spatial relationships, compared to just classifying.
Interesting. And then the Dano models, Dano V2 and Daigi 3.
These are kind of the cutting edge of self-supervision. They learn without any human labels at all.
How do they do that?
They use this teacher-student approach, basically learning to recognize different augmented views of the same image as being similar. Dino V3 especially is massive and was designed to create really stable, dense internal features. That might be key for geometry.
Okay, so a supervised model versus the 3 different flavors of self-supervised models. And they didn't just use the standard block shapes, did they? They used different kinds of data.
Right. They wanted to test robustness. They used 3 synthetic data families. First, the classic Shepard-Metzler objects. Those 3D block structures.
With different difficulty levels.
Yeah, an easier version with constrained rotation, and then a really tough free rotation version where the objects could be spun any which way.
Okay, what else?
Second, they used text, which is interesting. They had normal English words, random characters, and even artificial symbols, testing 2D spatial reasoning, really.
And the third type?
Photorealistic scenes. Think tabletop scenes with like 3 to 6 pieces of fruit rendered from slightly different camera viewpoints.
Why the fruit scenes?
To bridge the gap towards real-world images, they varied the camera angle difference, say 90 degrees versus a tighter 30 degrees, to see how things like occlusion affected performance. More occlusion makes it harder, right?
Got it. Okay, the stage is set. Let's get into the results. Finding number one seems like a big deal regarding how these models learn.
It really was the first major finding pretty much across the board. The self-supervised models CEP-E, DINOV2, DINOV3 were significantly better at this than the supervised ViT.
Wow. So the model trained just to classify things, the supervised one.
It seems like its focus on invariance, on discarding orientation to classify, really hurt it here. It threw away the geometric information needed for mental rotation.
Well, the self-supervised models, by needing to understand the image content more deeply, perhaps?
They ended up preserving more of that structural, pose-related information, whether it was matching text like CLIP or matching augmented views like Dino. Their training forced them to capture a richer representation.
That makes a lot of sense. Now, you
Yeah.
mentioned the text tasks were interesting. There was something specific about Dino v3.
Yes, this was quite the aha moment. You'd expect CLIP to do well on text rotation, right? It sees text captions during training, so it develops some optical character recognition, OCR-like abilities.
For sure, that track.
But Dino v3, which never saw text labels or captions during its training, it performed almost as well as CLIP on these text rotation tasks.
Wait, really? How? It learned to mentally rotate letter shapes without ever being taught about letters.
It seems so. It suggests its self-supervised method is just incredibly good at learning complex visual structures, period. It learned the spatial relationships within character shapes implicitly, just by looking at pixels and consistency. An emergent ability, really.
That's genuinely wild.
Yeah.
But not all self-supervision led to success here, right? There was a counterexample.
A very important one, Meta's MAE model, masked autoencoder.
Also self-supervised, but different.
Yes, its goal is reconstruction. You mask out parts of an image, and the model tries to fill them back in. And MAE, well, it completely failed at mental rotation, at any layer.
So just learning to reconstruct pixels isn't enough.
Apparently not. It doesn't seem to force the model to learn the kind of deeper geometric or pose-aware structure that Dino or CLIP pick up. It shows the type of self-supervision really matters.
Okay, so self-supervision like Dino's or CLIP's wins for this task. Now, let's get to the second major finding, which sounds like it changes where we should even look inside these models.
This is where it gets really fascinating, I think. Finding to the intermediate layers, the ones inside the network, not the final output layer, consistently performed better.
Better than the final layer. That seems counterintuitive. We usually think the final layer has the most abstract, complete understanding.
Right. We sort of assume information gets progressively more refined. Early layers get edges and textures, later layers get objects, the final layer gets the concept. But for this spatial task,
What happens?
performance seems to peak somewhere in the middle layers, maybe around layer 16 or 18 in these big models, and then it actually declines towards the final layer.
So the model figures it out, but then forgets or abstracts it away.
That's exactly what it looks like. The final layer, optimized for that general invariant classification, seems to actively filter out the specific pose information that was clearly present just a few layers earlier.
Wow. Is there a specific example of this, like on the really hard task?
Yes, the toughest one was the Shepard-Metzler free condition, totally unconstrained 3D rotation, extremely difficult. Only the biggest model, Dino v3 Huge, showed any real ability to solve it. And critically, that ability was found almost exclusively at layer 18.
Not the final layer.
Nope. If you only looked at the final output, you'd conclude Dino v3 failed that task too. The success was hidden deeper inside.
And this knowledge wasn't just some abstract concept. It was tied to the spatial layout, right? Something about how it processed the image parts.
Absolutely. They checked that. They compared using the model's global summary token, the CLS token.
The bit that usually holds the final classification idea.
Yeah. Performance was way worse using that. The good performance came when they used the average of the patch embeddings.
Meaning the information associated with different locations in the image.
Exactly. It suggests the model is tracking the geometry by looking at how individual pieces or patches of the object are oriented and positioned spatially.
And they could actually visualize this internal geometry.
They did. It's quite striking. They took the embeddings from a high-performing middle layer, like layer 16 in Dino v2 or Dino v3. They fed in an object rotated smoothly through 360 degrees.
And watch what the embeddings did.
And instead of being random, the embeddings traced out this beautiful, smooth circle in their high-dimensional space. The position on the circle directly corresponded to the object's rotation angle.
A literal circle of rotation inside the AI's representation.
It's the perfect visual of equivariance in action. The model's internal state mirrors the rotation of the input. That knowledge is there, clear as day, in the middle layers.
Before the final layer squashes it down for classification.
Exactly, it gets abstracted away.
That's incredible. It implies these models are learning much more nuanced stuff than we realize, but the standard way we use them hides it.
Definitely. And the third main finding connects this back nicely to us, to human cognition.
How so?
The way task difficulty scaled for the AI seemed to mirror how hard these tasks are for humans.
Oh, interesting. Like reaction times.
Sort of analogous to that, yeah. For the Shepard-Metzler objects, the bigger the rotation angle between the pair, the harder it was for humans. And similarly, the AI's accuracy dropped predictably.
Okay, that makes sense.
And for those photorealistic fruit scenes, accuracy was lower when the camera angle difference was small, like 30 degrees compared to 90 degrees.
Because the 30-degree view would have more occlusion, parts of the fruit hidden, making it harder to mentally reconstruct the full shape.
Precisely. Just like it would be for a person. It suggests the AI isn't just finding some weird statistical shortcut. Its internal representations face similar geometric constraints and challenges as our own spatial reasoning.
So it's genuinely grappling with the 3D structure in a way that reflects the difficulty we experience.
It seems that way, yeah.
Okay, so let's pull this together. What's the big picture here? It seems like these models can do this complex spatial stuff.
Yes, they implicitly encode a lot about 3D structure and viewpoint, but critically, the training method matters immensely. Self-supervision, especially dino style, seems key to capturing that information.
And crucially, we need to look beyond the final output layer to actually find it.
That's the other huge piece. So the key takeaways for you listening are probably twofold.
Yep.
First, if you need an AI model for tasks involving spatial reasoning, pose understanding, geometry, self-supervised models, particularly Dino V2 or V3, look like a much better bet than standard supervised ones. They just preserve that structure better.
Because they weren't forced to become purely invariant.
Right. And second, maybe the more practical point, don't just rely on the final embedding or classification output for these complex tasks.
You have to probe deeper.
You really do. That critical spatial information often peaks in the intermediate layers. You might need to extract features from the middle of the network to tap into what the model truly understands about geometry.
It's a call to rethink how we evaluate and even use these models, isn't it?
Absolutely. Maybe we need architectures or methods that don't discard this valuable information quite so readily towards the end.
Which leads to a final thought, perhaps. If this vital geometric reasoning, something fundamental to how we interact with the world, is being learned and then essentially filtered out by the final layer, it makes you wonder, doesn't it? What other complex kinds of reasoning, maybe causality or understanding sequences of events or really deep concepts, might also be forming in these hidden middle layers only to be lost in the final abstraction? What capabilities are we missing by only looking at the very end?
That is a big question, isn't it? Something to definitely think about.